By the late 19th century, the scientific community believed the work of physics was essentially finished. They saw the universe as a giant, predictable machine. This confidence came from classical mechanics. For centuries, these laws had been applied to almost every observable event in the natural world, and they had never been proven wrong. Whether you were measuring the rhythmic swing of a pendulum or calculating the force of a falling object, the math was flawless. These same rules scaled up perfectly, governing the precise orbits of planets and the motion of the stars themselves. Because this system worked for centuries, physicists assumed these rules were universal. They believed that if you looked closely enough at anything, you'd find the same predictable mechanics at play. But as technology allowed them to look closer than ever before, they discovered that their universal rules were actually quite limited. At the dawn of the 20th century, new experiments began to reveal a world that was previously invisible, the realm of microscopic particles. Scientists attempted to take trusted classical formulas and apply them to new discoveries on an atomic scale, specifically studying how atoms emit light and radiation. The results were a shock. Calculations for planets failed for these tiny particles. The old model predicted atoms act like tiny billiard balls, but experimental data showed something much more complex. The macroscopic rulebook simply stopped working. They encountered specific phenomena, like the way light interacts with metal in the photoelectric effect, or the spectral distribution of blackbody radiation. These weren't just small errors, they were physical events that classical physics could not explain. These anomalies proved that classical physics wasn't wrong, but it was incomplete. Its accuracy was strictly tied to the scale of the object it was measuring. This realization caused a genuine crisis. The fundamental building blocks of reality were behaving in ways that violated the core laws of physics. As more experiments were conducted, the evidence became undeniable. Scientists couldn't simply ignore these glitches or patch the old math. The microscopic world demanded a different approach entirely. It became clear that microscopic particles don't follow the same path as a falling apple. They move and interact in unpredictable ways that require a completely different mathematical language. To move forward, the scientific community had to do something radical. They had to accept that the rules for large objects don't apply to the small, and they began building a new foundation from the ground up. This new framework is called quantum mechanics. It is a modified system of physics specifically designed to account for the behavior of microscopic particles. We now understand that the universe operates on two distinct sets of rules. Because classical physics failed to explain the atom, quantum mechanics has become the sole basis for our understanding of all physical phenomena on an atomic scale. While classical mechanics remains our tool for macroscopic bodies, like cars and planets, quantum mechanics is the only reliable way to explain the microscopic world. Identifying this divide allowed us to move past theoretical confusion and start using these microscopic rules to build new technologies. While these concepts seem abstract, they are actually the foundation for the technology you use every single day. Take the semiconductor devices inside your smartphone. The way they process information relies on the behavior of electrons, behavior that would be impossible to control if we only followed the old classical laws. This understanding also led to the development of optoelectronics and laser devices. By mastering the way atoms emit energy, we can use light for everything from high-speed internet to industrial cleaning. It even extends to biotechnology. By applying quantum mechanics at an atomic scale, scientists can now analyze and modify the structure of cells and DNA. Today, these same principles are the driving force behind nanotechnology, the ability to engineer materials and machines at a scale of billions of a meter. The quantum world remains invisible to our eyes, but its discovery is the absolute foundation powering almost everything in our modern lives.